All right, so welcome everybody to our network security class. Thank you for being here with me again. Like I mentioned, I have updated the due dates inside the class itself. They were all actually right on the syllabus, but I had not put them into the assignments themselves. So if you go down here and look at Packet Tracer 1491, you should see it is now due on April 9th. So all of those are good. I've actually graded a lot of the assignments that were due. Of course, I'd have to pick the one I hadn't graded yet. But I'm pretty sure I've graded like up through, yep, there's 8512. I've graded everyone there. And I've stopped at 865. So, but these are actually were due last week. So you're not too far behind. The other thing, don't forget, later in this class, there's not a huge number of assignments. So you do have time to catch up. But I do ask, if you have not done any of the packet tracers, please do catch up, so I don't have to do 5,000 packet tracer gradings at the very end of class. We also need to remember that for this class, I'm asking you to do all the packet tracers, all the module exams, the packet tracer skills assessment, and the final exam. That's all I'm asking you to do in this class. So it is not a very difficult class for you to get accredited in. I hope you've seen that this class does add some really good things that you can put into your other class, especially your CCNA 3 class. You know, the items we went over last week, where we were talking about different ways of doing securing device access and even administrative roles, where we were able to create different levels of commands. That's the kind of thing you can teach in your CCNA 3 class as additional content, using that role-based, you know, looking at our role-based access, you know, super views, root views, all those. So make sure that you know that that is available. I'm not going to spend a lot of time today in the access control list or the firewall technology sections, or even AAA, because they're very easy to understand. The ACL is just a review of stuff that you've already done before. So that's not a big deal that we need to talk about. But we do need to talk about this zone-based firewalls, because this is something a little different that you haven't done before. So we're going to look at how, instead of just looking at traffic in terms of a source destination IP address and permitting and denying it that way, we're going to look at creating what are called zones and applying security policies to those zones. This is how most modern firewalls do it. And from Cisco's ASAs that we'll discuss in a couple chapters to Palo Alto's individual firewalls, they use a zone-based setup. So traditional model, you've got a firewall policy applied to interfaces, but in a zone-based model, you apply the policy to zones and identify traffic moving between those zones and set up different policies. For instance, if we look at this right here, we may have a private zone, a public zone, and a DMZ zone. And if we have this set up, we would set up a set of rules that would say anything from the private zone can go either to the public zone or to the DMZ zone. And also, if it originated in the private zone and went out to the public zone, the firewall will keep information about that session and will create a ACL to allow that traffic back in. So in other words, you don't have to create an ACL for out and in. You're basically going to say, if it's coming from the private zone, going to the public zone, we will allow it, and we'll allow that traffic to come back in. If, however, it was traffic coming from the public zone trying to go directly into the private zone, we would say, no, that traffic's not allowed. Likewise, we may set it up to where the DMZ zone can go to the public zone and come back. And we may even set up some individual items where the public zone, if it matches certain traffic information, could go into the DMZ zone. Does this mean we never use source destination IP address as part of our classification? No, it does not. But it's only one part instead of the only part that a classic firewall uses. So they're not dependent on ACLs. By default, the posture is blocked. So if you don't set it up to allow it, it's not going to be allowed. So if you create these zones and don't make any changes and don't allow any zone pairs or don't allow any zone policies, traffic will not be allowed to cross. Policies are easy to read and troubleshoot because they use a common classification language. I'll argue with that a little bit. They're easy to understand. When we get in actually making it, it's going to look confusing, but as we walk through it, it'll make a much more sense. it looks much more difficult than it actually is once you look at how it's set up. But virtual and physical interfaces can be grouped into a zone, and policies can be applied to what is called unidirectional traffic. So if the traffic's only going one way for some reason, it can have a zone pair set up. We'll talk about that. So what do we need to do? First, determine our zones. So we need to know what is our secure area, what is our unsecure area, what are our somewhat semi-secure areas. We're going to establish our zone policy, so a source destination zone, and set up policies. If most policies are, our policies are typically set up to be for traffic that will go both ways, will flow both ways, bidirectional. In other words, it originate inside, go out, and need to come back in. We have a thing called zone pairs that can be used if you're wanting to allow just unidirectional traffic to go out. So if it's going to go one way versus the other. Let me pull my chat up here. Amar, no, it does not, unless you set it up that way. So you're saying there's an interface between private and public zone. No, what you could do is you allow the private zone to go to the DMZ, and you allow the public private zone to go to the public. You also would probably allow DMZ to go to public, but you would not allow the DMZ to go to private because you want the DMZ to not be able to get into your quote clean or secure network. Now, traffic from the private can go to the DMZ, and then that traffic that originated in private will be allowed back in, but we're not going to usually punch a hole between the DMZ to the private. The reason we use the DMZ is in case we have something like a web server, or we have a head-end mail server that we want to use that has to be accessed from the internet. That allows us to punch a hole in this firewall to allow that internet traffic to come through the firewall into the DMZ without having that traffic come into our completely clean private network.
Okay. Can I ask a follow-up question on that, Kelly?
Yes, definitely.
So what's the primary goal of DMZ zone? Is it to contain all the public-facing devices like servers, or is it to secure the private zone?
It is to host those public-facing services. That is exactly what it is. Go ahead, Amar.
Yeah, please go ahead. I'm sorry.
No, but I'm saying, and by doing that, you protect your private zone, because otherwise you would have to put you'd have to put those servers in the private zone and punch a hole through the firewall into those. By putting them in the DMZ, they're out there in their own gray area that's not super secure and it's accessible from the outside world.
Thanks.
Okay. The other thing we do, anything on the DMZ, let's say it's a web server, remember, we're going to harden it. We're going to turn off everything that's unneeded on it. We're going to make sure it does just that one job, and that's it. There's even a thing you'll learn about down the road where in this DMZ, if these machines were on a switch together, we would put them in what are called private VLANs, so that even the machines in the DMZ can't talk directly to one another. So that's some things we can do to try to make the DMZ even more secure. But you are correct. We put our public-facing services in the DMZ to help protect our private zone from those.
Thanks, Kelly.
Very good question. Excellent question. So we also need to define our physical infrastructure. So what's going to be in what zone, and then even subsets within those zones. So how are we going to design traffic policies between those? So we could have a setup like this, which is a very simple inside-outside, so dirty and clean. We could have a DMZ like this perimeter, which is just another name for DMZ. So you've got your outside, inside, and a DMZ. Here's an example of, actually, many people do this because it actually allows you to put in two firewalls and increases security in some ways, because you got the outside, the perimeter, then the inside. And then in high availability environments, you may do the same thing and have multiple firewalls, so that you're able to have redundancy in case a firewall fails. We had an issue with a firewall today. It would not update its antivirus and or any of its basically malware files, and we had to do some issues. We do have them in redundancy, so we could have switched over to the other one if the problem had not been fixed. But many environments try to run multiple firewalls so you don't have a single point of failure. And then here's a very complex firewall, and this is where you're breaking every single part of your network into its own little DMZ, so to speak. And you can see how this would really increase your administrative overhead because you've got all these zones. The other thing we have found is if you make things too complicated, you can actually get yourself in trouble. The KISS principle does apply, keep it simple, stupid, because the more complex you make it, there is a better chance you're going to make a mistake in your zone configuration. Let's look at it. Now, when we set up our zone policies, we've got 3 possible things that they can do. Inspect it for stateful packet inspection, which basically means if it goes out from one zone and you're allowing it to go to another zone, it will be allowed back in. Drop, which is like a deny statement, and pass, which is pass. But the pass action does not track the state of the session. So inspect does allow it to pass and will track the state. So be aware, if you want it to be able to poke a hole back in, coming in, we want to inspect, not just pass. Here's basic security. Now, this next chart looks confusing, but it's not that difficult. So let's look at what we've got here. If neither interface is a zone member, the action is to pass the traffic. In other words, if there's no zone policy, it just passes traffic like a normal router does. If both interfaces are members of the same zone, it will pass the traffic. In other words, they're considered to be equal in security level, so they're in the same zone. If one exists in a zone and the other is not, it will drop, regardless of whether or not a zone pair exists. In other words, does not matter. If one is in a zone member and one is not in a zone, it will drop that traffic. And if both are in a zone pair and a policy exists, the action is either inspect, allow, or drop as defined by the policy. So let's look here. Source member, not part of a zone policy, zone ZPF, not part of it, no zone pair exists, pass. So just like a normal router works. If one interface, the source is a member of the zone and the destination is not, you drop it. Because remember, our default security policy is drop with the zone policy, ZPF. This is just the reverse of the one above it. So the source interface is not part of a zone. The destination is, you drop it. If they're both part of the same zone, by the way, the reason they put private here is they're telling you it's part of the zone, and the zone it's part of is the zone called private. So if it's part of private and it's going to private, it is allowed. If it is private and it's going to public, but there's no policy and there's no zone pair set up, okay? And a zone pair is only for unidirectional traffic, not bidirectional traffic. That's why zone pairs exist. Then you drop it. If, however, the source is in private, the destination is in public, and you've set up a unidirectional zone pair, you will pass it. We don't really go over zone pairs as far as configuration, but it's a function that's available inside of ZPF. I was actually trying to determine what would be a type of unidirectional traffic that would be needed between zones. And I couldn't for the life of me think anything. Can anybody else think anything for unidirectional traffic? That traffic would originate on the inside and go out and not go anywhere else? Not need to come back in?
I can't think of anything.
What about if you were logging to AAA or something?
Possibly
Right.
syslog. Yep, that's possible, Bill. Maybe some type of syslog traffic that would, yeah, that is possible. Maybe some type of SNMP. Good point. It could be maybe an SNMP logging or syslog logging that would be possible. Yeah, that's a good point. Because it'd be using UDP, so it wouldn't be a connection oriented. It would not be a connection oriented connection. So yeah, that's a good point. Could be that. And then finally, this is how we're most likely going to use zone-based firewalls, and that is we'll have member of one zone, in this case private, going to another zone public. We've created a policy, and we are going to inspect it. And so we're going to do inspection, which basically says we're going to look at it and do what is put into our policy. Now, the self zone is a different thing. This is for anything that originates from the router or goes to the router. Because of this, you'll notice there's a very different setup here. If it's the self zone going to a member of another zone, it's going to be allowed to pass. And that is because we need to be able to have control traffic, like routing traffic, those routing table updates, routing protocol traffic, those types of things. If it's a self zone going to a member of another zone and a zone pair, it's going to pass. If it's self zone going to a member of another zone and a zone pair exists and a policy exists, it will inspect it, which again still allows it to pass. Well, depending on what your actual policy says, it's going to allow it to pass if your policy says so. And so most of what you see here is, you'll notice anything that is from the self zone or to the self zone pretty much is allowed to pass. And that is to make sure that our traffic going to and from the router and all these other protocols like OSPF, EIGRP, SSH, traffic to and from the device itself is allowed to pass our zone-based firewall. Without this special self zone, we can lock ourselves out of our router because we would have to go in and set up the ability for routing protocols to pass between devices and all of those other management protocols. So let's look at configuration. Now this really does look confusing, but it's not. We're going to go with a simple setup. We've got a private zone and a public zone. We're going to create our zones. We're going to identify our traffic with what's called a class map. In other words, we use the class map to define the class of traffic. We're going to decide what we're going to do with it with a policy map. And then we're going to identify the zone pair and match it to a policy map and assign zones to the interface. So let's create our zones. First off, just think of a name for the zone. In our case, we've used private and public. All right. Security zone private. You'll notice it goes into a sub-configuration mode we've never seen before, which is security zone sub-configuration mode. And zone public. So private, public. We've got our two zones. Rule one, first thing we do. We're then going to classify our traffic. So we do that to identify our traffic. We use a class map. So class map type inspect, and we've got two things we can do when we create this class map. We can either say we want to match any of the items we're going to put in the class map. In other words, if it matches any one item in the class map, it will be acted upon. Or we can say match all. It has to match all items in the class map. Okay. And that's our name. Now, once you put this in, once you make this decision, match any or match all, put in the name, you go into class map sub-configuration mode. And then at this point, you put in what needs to be matched. Now, you can do a match to an access group, to an ACL. So you can do it by source destination IP address. All right. You can do it by protocol name, HTTP, HTTPS, DNS, TCP, any of those. And you can actually match another class map. And so you can actually put class maps inside of class maps. For our example, we're going to make it really simple. We're going to say HTTP traffic is going to be allowed to cross R1 from private to public. So we're going to create a class map that says match any of the items below. It's going to match this class map of HTTP traffic. So if it's HTTP, if it's HTTPS, or if it's DNS, this particular zone-based firewall is going to act upon it. Okay, I'm going to stop here for just a second. You understand what's going on here?
Yes.
Okay.
It's just matching the traffic, right?
Exactly. Just match. This is the traffic that will be acted upon by this zone-based firewall. Correct. Now, once we define what's going to be acted upon, we need to define an action. We do that with our policy map. So the policy map will tell you what action is going to be done with this. So we do policy map inspect, policy map name, and then we'll go into policy map subconfig, class type inspect, and that tells you this must match our class map name. So it says inspect anything that matches this class map, and then we're going to put our rule in it. We're going to either inspect it, which does state-based traffic control, drop it, or pass, which is stateless and would not keep up with. Now, the problem with this is if you do pass, It won't put that hole back in and come back in. So be careful with that. That's why most of the time we're going to do inspection, to be quite honest, especially anything that's TCP based. We'll do inspection. So this says policy map to inspect prib to pub policy, so private to public policy. Anything that matches this class map, inspect it. Okay. So it's going to keep up with the session and connection information for TCP and UDP traffic going through this. Well, in this case, it'll only be TCP because it could be UDP because we got DNS in there. We did do DNS, and DNS is both TCP and UDP. We then match the zone pairs to a policy. So here we go, zone pair security, zone pair name, source zone, destination zone. So in our case here, it says zone pair security, prib pub, which is our very first, actually that's a name we're giving it. We're giving it the name prib pub. And then we're saying source is private, destination is public. And then we're going to take that policy map that we just created and put it right here and say, this is the policy map for our zone-based firewall. So again, we go back up here. We identify our traffic with the class map. We define our action with our policy map. We identify our zone pair and policy to that by applying the policy map to the zones. So anything going from private to public, we apply this policy to. And then we final thing is kind of like an access control list. We have to define which sides, or not really, we got to decide which one is in what zone. So we're going to say that gig 00 is in private, 0000 is in public. Now, any traffic that is HTTP, HTTPS, or DNS, which originates in the private zone and goes out to the public zone, will be matched and will be allowed back in because it originated inside and maps our zone-based firewall. Any other traffic will not be allowed in. So if you think about our little home routers at home, they're actually running zone-based firewalls. They're very similar to this because they're saying anything that originates inside and goes out, will let come back in. Otherwise, we're not going to allow it in at all. So if you ever wondered how your home router is doing it, they're really doing it with a form of zone-based firewall. A couple ways we can look at it. You'll notice this is one of the few where you actually have to do a show run pipe begin class map. We can look at our class map right here to show what is matched. Then we can look at our policy map to make sure class default, inspect traffic to make sure it's actually matching that. You'll notice that's something that's in there by default. If you don't, at the end of it, basically says anything that doesn't match this, drop it. So we're not going to allow any traffic out but HTTP, HTTPS, and DNS. We got our two public-private zones. We've got our policy we've applied to those zones, and then our interfaces are in the correct zones. And then if you really want to dig deep, you can go show policy map type inspect zone pair sessions, and it will show you the zone pair pub prib pub, and it will show you the policies there, and it will show you what's being matched, and it'll showing you each one that's actually being acted upon. So you'll see in this case, there have been no packets in DNS, 12 HTTP, and 5 HTTPS. And then this will show you that it's actually keeping up with an HTTPS session that originated inside and is now being allowed back in. You also can look at your class map. So show class map type inspect. It'll show you that. Show zone security. Show you your zones. Okay. So it looks confusing, but it's really not that bad once you just get down those 5 steps. So create the zone, identify the traffic with your class map, to identify your action with your policy map, identify your zone pair, match it to your policy map, and then assign your zones to it. All right. So several of you have done the lab or tried the lab in this one. Do you have any problems with it? Have any issues?
No, it was pretty self-explanatory.
Yeah, it really is. I do think it's important for you to mention to your students that this is how their home routers work. This is something that's very common, and it's not that unusual. Notice how much easier this is though than defining all of the IP addresses. We don't even care what the IP address is on the inside, do we? In fact, there could be 4 routers inside of this, and we don't really care because anything that comes in on that gig 00 is considered from private. So, Corey, you're just gonna say something?
No.
Okay. Any questions? If not, I'm gonna jump on to IPS. This is again very simple stuff for you. What's the difference between IPS and IDS? Anybody tell me IDS versus IPS?
One is for detection, the other one is for prevention.
Yep. So this is intrusion detection system. When I say intrusion detection, and IPS is intrusion prevention. So what do they do though? Yeah, one is detection, one is prevention, but how do they differ from one another?
Does one log an event and the other one actually notifies somebody that something's going on?
Well, this one both of them can notify and log, but the difference is this: intrusion prevention can act.
Yeah, he tries to do something.
Tries to do something. So it can either try, here's a great example. Cisco for years and years was taught about the self-defending network. So if you plugged a machine in that had a malware on it, the system could see that and immediately take that and either shut the port down, or it could also look at a device and say, hey, it has an out-of-date antivirus signature on it, and move that port that it's connected to into a remediation VLAN until it updates its antivirus. So intrusion prevention can act and not just detect. Having said that, there are some questions about IPS, because if IPS gets it wrong, sometimes it can start blocking things that shouldn't be blocked. Here's a 0-day attack. Everyone knows what those are. Basically an attack that no one knows about. But intrusion detection systems sit there and look and can send information to the management console and monitor it and say, hey, there's some type of attack going on, like snort. Snort is not ES. So it can basically tell you about it, but it doesn't try to do anything. IPS actually attempts to do something. So if it sees it, it will maybe send it to the bit bucket. It will either try to stop the attack itself, or it will try to in some way remediate the attack. As we're getting further into networks that are being attacked by AI and defended by AI, we're going to see more and more of these IPS systems that are AI based, that are just, quite honestly, we as humans cannot react as fast as an AI can. And so it's going to be interesting to see where that goes coming down the road. But here's the bad news. It says it puts it in the bit bucket, and IPS can, but the negative is if it gets it wrong, it's putting legitimate traffic into a bit bucket. So IDS, again, advantage, no impact on the network, no latency jitter, no impact there if there's a sensor failure, no network impact if there's an overload. Disadvantage, it cannot stop packets. It does need to be tuned, which is a big thing for the correct response. That's true of both of these, though. They both need to be tuned to have true positives and true negatives, and no false positives and false negatives. IPS can stop trigger packets, and it can use what are called stream normalization techniques. So look and see what's normal and attempt to define that and allow that. However, with an IPS, depending on how it's set up, if an IPS is overloaded, it could actually cause the network to go down, or it could impact the ability of the network to send traffic through it. So just be aware, there are advantages and disadvantages to both. How many of you have IDSs in your environment or IPSs?
What,
Not many people
classroom?
do because they're so expensive. You may have an IDS, but maybe probably not IPS. So here's an example of putting one in line. Okay. So we put an IPS in line on both sides, typically between our external firewall and the untrusted network and our internal network, looking at data between these. Another issue that a lot of these have is that obviously if data is encrypted, it can't look into it. Palo Alto actually has a way with their firewalls to decrypt SSL traffic and look inside of the SSL traffic going in and out of your network. That opens some true, you think about some really strong ethical questions about privacy. Open SSL traffic. Having said that, you have no, most network policies state that you have no expectation of privacy on the network, that you're using if it's a corporate network. But that is something that does happen. Cisco makes a firepower appliance that will do this, the ASA firewall and an ISR router, and there are other next gen virtual IPSs that can be put into our environments. They need to be fast. They need to be able to process information very quickly. And then they still have to be tuned to allow them to determine what is normal traffic and what is not normal traffic. So it's a lot of work to make an IPS and even an IDS work correctly. The other thing is, in a switch network, you're going to have to use what are called span ports. Otherwise, you won't get the traffic. So, this switch, the PC on the left talking to the PC on the right, with normal switch operation, that frame is not going to go to the IDS at all. And so you have to set up a span port to send copies of that traffic to the IDS. To do that, that means your span port has to be fast enough to handle traffic between all of your devices, which typically means you're going to have more than one IDS device or IPS, which then means you're spending a whole lot of money. So you can see how these are really good, but they can get expensive and they're hard to use because of that. You put them in line, that's great too, but again, then they can affect your network performance. So there's a lot of kind of give and take with IPSs. You can run this on a Cisco IRS router or ISR, Cisco router. There are actually ways of loading Cisco intrusion prevention system signature files onto all of the ones that are shown here. It's not really supported now as much, although we can do Snort IPS on our newer 4000 series. Cisco bought Snort. I don't know most people realize that, but they bought Snort and it's their product. But you can do it. And then if your router is fast enough, it can do it. You just have to be aware that the router has to be quick enough to handle it. Yeah. So Cisco's iOS IPS is all these old devices, and they're really not even available anymore. The newer one works with Snort, and it's an engine that many of us are familiar with. It uses a standardized Snort database for malware and for signatures. So you have to keep your signatures up to date. You'll notice there's a container. Typically what happens is this thing actually runs as a little container inside of the router itself. It's really just a little Linux box type thing that runs inside the router itself. You also can use Cisco's Talos, and that Talos will deliver the signatures directly to Snort. But you need to determine, are you going to run it in IPS mode or IDS mode? So you can do it, but this is going to greatly impact the ability of your router to move traffic. So you need to be aware of that. Which is where we get to these Cisco system requirements. You've got to have at least 8 gigs of memory, 8 gigs of flash. You've got to have a K9 license. The 4200 series does not even support Snort implementation. And then you got to buy either a community rule set or a subscriber rule set. With community rules, you're only getting the ones that are put out by the Snort community, which is basically open source signatures. And the subscriber rule is you're getting the community rule set plus the individual ones that Cisco is writing as part of their security team. Typically, the subscriber rule set is faster in terms of getting out new signatures for new attacks. Not always, because the community is very good too, especially with Snort, because it is and has been an open source product for so long. It's funny, pulled port is the rule management application used to download Snort updates. And OINC code is free with registration. Okay. But you got to have an OINC code in order from your snort.org account. They really played up the pig thing. I mean, let's just be honest. So pulled port is the rule management. But you got to admit, that's pretty good. I mean, that's pretty funny. So how do we monitor our network? Well, we can do a network tap, which is literally a device that sits inline and sends us signals to our monitoring device. There are network taps that are for wired. There's those for excuse me, drawing a blank here. Wired, wireless. There's those for fiber optic cables. All these taps sit between basically a network firewall and an internal router, and then you can pull information off and send it to your IDS or IPS. We often use this, what is called traffic mirroring with span ports. And so we figure out where the ingress traffic and egress traffic is, and we do a source span and a destination span. So in other words, you say that the span port is gig 01, the destination span, and source ports are 0102, so that any traffic ingressing or egressing from 01 to 02 will also be replicated out the destination span port. There's even a thing called remote span or RSpan, where you can, typical span is replicating the traffic on a port on the same switch in which the traffic originated. Remote span can actually send it to another port in on another switch. So that's called RSpan. So you can use, like I said, you can put your management server, your IDS sensor on another complete switch and do RSpan. Just realize that means all that traffic's being replicated and sent across your network to that RSpan port. You also can overwhelm the port that is your span port, so you need to be careful with that, because if that's a gigabit on 0102, and you try to send it out to a gigabit port, you can overwhelm it. You'll notice in our example here, they've given a fast Ethernet or 100 megabit port and a fast Ethernet port going to a gig port. So they're trying to show you that you would want to make sure that the span port has the bandwidth to handle any ports that you're gonna span to it. So pretty simple to do. Monitor session number, interface, and VLAN. So you can do monitor session 1 source interface fast Ethernet 01. And then if you want to span it to 02, you just say monitor session 1. These do have to match in order for them to be able to send information. Destination interface fast Ethernet 02. So PC is connected 01 and IDS is on 02. The IDS would capture all traffic going into or out of 01 and send it to the IDS. Show monitor will show you those span ports. Show the source and destination ports. And then if the packet analyzer is on a different switch than the traffic that is being generated, you have to use what is called RSpan. And typically we create an RSpan dedicated VLAN that is just for that traffic to traverse our network or our building, wherever we're doing it. The way network design is today, if you were doing RSpan, you would probably have that inside of the building. It would not cross across building to building traffic. Just because we don't do VLANs to every building now. We basically have our buildings are VLAN designated points or VLAN endpoints. Okay, any question on IDS and IPS and the difference between them? Well, folks, that's really all I had for today. Are there any questions about anything I went over? Any questions about zone-based firewalls? Questions about intrusion prevention systems versus intrusion detection systems? Any questions about access control lists that you've gone through at this point?
I'm good right now.
Any questions at all? Everybody's just trying to catch up. Realize class does run through May, so you've got a little bit of while. You got some time. We will have class again next Wednesday. So please bring your questions. We'll go over and look at IPS operation implementation, endpoint security, and some layer 2 considerations as we keep moving on.
Thanks a lot.
All right, everybody, I'm going to stop the recording.